Okay, so this is example problem 14.4. Again, we have a distributed load here, and we have a I-beam, a W30 by 99, hot-rolled structural steel flange shape. W30 by 99 is used as a simply supported beam. The span of 32 feet is shown. The beam supports a superimposed uniformly distributed load of 4 kips per foot in addition to its own weight. Calculate the maximum bending stress. Okay, so we're given a W30 by 99 steel beam, a length of 32 feet, and its loaded as shown. What we're supposed to find here is the maximum bending stress. Okay, so first, we need to know how much the load is due to the weight of the beam. So, a W30 by 99 structural steel beam is about 30 inches high and weighs 99 pounds per linear foot. Okay, so the first number, the W30, the 30 is roughly the height of the beam, in this case 30, and the by 99, 99 is pounds per linear foot. So if we're going to superimpose those loads, what we have is the 4,000 pounds, that's this 4 kips per foot, plus 99, and what we have is 4.1 kip per foot. That is the loading. Now again, we can go to Appendix H, because this is a simply supported distributed loaded beam, and find what the equation is for a maximum moment, as we did in the previous example. So that's W times L squared divided by 8, and we get 525 kip foot. So therefore, the maximum stress equals the maximum moment divided by the section modulus. Okay, when I go to Appendix A and look up this W30 by 99 beam, I can find what the section modulus is. Section modulus is displayed in Appendix A as 269 cubic inches. Therefore, my maximum bending stress is 23.4 KSI. Next problem. In this case, we have a steel pipe, an extra strong steel pipe, having a nominal diameter of 127 millimeters, is to be used as a simple beam with a span of 7 meters. The pipe supports a concentrated load at the midspan. Okay. Calculate the maximum bending stress due to the weight of the beam alone and due to the concentrated load alone. This sets up the concept of superposition. But anyways, given extra strong steel pipe, 127 millimeters in diameter, loaded and supported as shown, find the maximum bending stress, FB, due to the weight alone, and then due to the load only. So, due to the weight, if we go to Appendix B, we can look up this pipe, okay, and it tells us that our section modulus is 115 times 10 to the third millimeters cubed. Make sure you go to Appendix B and find out where I'm getting this from. And then the mass of this pipe is going to be 30.9 kilograms per meter. So the first thing we need to do to solve it, well, obviously, besides getting the data we need out of the appendix, is to calculate the weight of the pipe. Weight equals mass times gravity. So in this case, it's 30.9 kilograms per meter times the constant of gravity, 9.81. And in this case, we get 303 newtons per meter. Okay, so therefore, M equals W times L squared over 8. Again, this is the Appendix H, beam 1. And from that, we get a maximum moment of 1,856 newton meters, and then calculate what our maximum bending stress is based on the maximum moment divided by the section modulus, gives us a 16.14 MPAs. Now, due to the concentrated load, again, we can go to Appendix H, beam 5, and then M equals PL over 4, which is the equation for the maximum moment. And I get 10,500 Newton meters. And then the maximum bending stress would be 91.3 MPAs. Example 14.7 was just talking about finding what our maximum allowable moment would be based on a maximum allowable bending stress. So in this case, we have a 6x8 timber pine. Our maximum allowable bending stress is 1,000 psi. So therefore, find the maximum moment. So again, we're taking advantage of Appendix E, properties of structural timbers. So for a 6x8, we can find directly what the section modulus is without calculating it. So the section modulus is 51.6. Therefore, the allowable moment equals the allowable shear stress times the section modulus. Therefore, my allowable moment is going to be 4.3 kip per foot.